Good morning, everyone. My name is Agnieszka Sitko, and I'm a data scientist at the Warsaw University of Technology. And together with me² group, we are developing a set of tools to somehow support the design of explanatory variables in our models. Together with that, we also want to work with visualization that will explain how our models works. And today I'm here to talk about the factorMerger package that we've developed. And the main idea of this package is to deal with factorial variables. So suppose you have a factor that has a lot of levels, and you may imagine that including this factor into the final model will bring a lot of information into the model. So eventually we may end up with the overfitted model. So we might think of finding some more general pattern into this inside this factor to provide overfitting. And this is what factorMerger does. It clusters levels of our factor. So probably you may be familiar with some algorithms that help you to understand the relationship between the response variable and factor variable. So I'll just give you an example why we're just so troubled about them. So suppose you have a factor called C with k levels and numeric response y. And in this example, we'll work with data from Program for International Student Assessment. We'll analyze students' performance in math in 3 European countries, Poland, Netherlands, and Belgium. And you would like to analyze the differences among group means of y. So for the simplicity, we'll assume that y is normally distributed, and k is greater than 2. That is checked in this case. So if y is normally distributed, you may say that this task is really pretty easy, because first you just need to run analysis of variance to detect whether any difference is present, and then you just follow up with a particular post hoc test that will detect where exactly this difference is located in the data. So if that's easy, then we just try it out. So we'll start with analysis of variance. The null hypothesis is that all means are equal in all subpopulation. And in our example, here's the plot that visualizes ANOVA. So for each country, we plotted its mean together with 95% confidence interval. And if those 3 intervals overlap, then we may say that the null hypothesis is true. However, it's not that visible, but the Dutch interval and Belgian one do not have the common intersection. So probably the null hypothesis will be rejected. And in fact, if you run also ANOVA and you get the p-value for that, ANOVA rejects the null hypothesis. But we are more curious than that, so we will also carry out a post hoc test. If you are not familiar with post hoc testing, the idea behind them is pretty simple. So first you have to take a given statistical test that is designed to compare means of the groups only, and then you just perform pairwise comparisons. And here's also the visualization, similar to the previous one, however a little bit different story. So in the y-axis we have all pairs from our data set, and we mark the difference in mean in each pair, also with the 95% confidence interval. The interesting point is 0 if 0 marked vertically. If 0 is inside the given interval, we may say that the difference is not significant. So in our case, we have 2 pairs that in fact share mean. These are Poland, Netherlands, Poland and Belgium. However, with Netherlands and Belgium, the story is different because 0 is outside the confidence interval. You may also use 2K HSD test in R to get the numerical results for that. So that's where the case gets complicated, because if we were to create some other partition of our data, it's simply not possible in this example, because in particular, you may not be able to say where to put Poland. Should be whether in the same cluster as Netherlands, or should be in the same cluster as Belgium. And that was only an example of 3 countries. So if we take all European countries, the case is even worse. So from theoretical point of view, you may observe a lot of pairs that are not consistent in result. Also, the visualization is kind of hard to read. I think you can spot Montenegro there, but that's it. What's more, we have fixed a significance interval. So that's maybe not such a big issue, but you get only one number from ANOVA, then people actually tend to not use p-values that much, so maybe we may think of something more structured. So now is the time for our package, and I will show you the same example, however plotted with our package. This is the final product of factorMerger, all European countries included. And factorMerger is already present on CRAN. This is how you install it and how you load it. Basically, to get the previous visualization, you have to perform on 2 steps. First, you have to run function merge factors on your response and your factor. Then just run plot on the object you obtain. So how do we get such results? So we implemented 2 approaches for merging. They are both hierarchical merging. One is likelihood ratio test based. The other one is leader merge regressor based. So in the first scenario, if you think of a problem of choosing which pair should be merged in a given step, you may probably just run likelihood ratio test and take the pair which gives you the highest p-value. So this is basically what is done in this algorithm. However, in each step, the reference level is the same, so it can be simplified to maximizing likelihood by its own. However, you may say that calculating this likelihood value is quite expensive. So if we do it a lot, then this may be really time-consuming. So we implemented also other approach that calculates likelihood ratio test statistic only once at the beginning, and we define them as the metric between 2 levels of the factor. And then, having this fixed distance matrix, we may just perform hierarchical clustering, either single linkage or complete linkage. And the visualization, the final visualization consists of 4 panels. I'll just tell you about 3 of them that I really like. The main panel is the factorMerger tree, and we denote it with colors the final clusters, also printed group means, and on the x-axis you have model likelihood. So basically each node in this tree, except from the leaves, represent 1 model. But eventually we have to decide what partition should be chosen, and it is based on the generalized information criterion with a specific penalty. And for each model in the merging path, we also calculate dynamically this GIC value, and we choose the model which has the lowest GIC value. And the GIC penalty is another argument that you can manipulate with. So suppose you have a high GIC penalty, you will achieve the bigger cluster. And the other panel is somehow a summary of response variables. So in single Gaussian case, we implemented 4 plots. These are group means with 95% confidence interval, box plot, however, not with medians, but with means, group frequencies, and 2K-HD test results. And we are not limited only to the singular Gaussian case. We also have multi-dimensional Gaussian case. And as you may see in this plot, you may also force the factor-merger tree not to space your nodes with that will give you the information what the effect would be on a given group. Also, we have binomial model with success ratio as a response panel, and survival model with survival plot. And in the most comprehensive approach, you just run function merge factors and then run plot function on it. However, each panel is a ggplot object, and we also exported them as well in a package, so we can generate plot on its own and manipulate with that. And I also want to thank NCN for funding this project. Thank you.